hang up and try again.
In this example, we're going to use factorial. A friendly reminder, a factorial of a number is a consecutive product of two numbers starting from 1 all the way to n. For example, 5 factorial, it's 1 times 2 times 3 times 4 times 5, which is 120. So in this case, we have a loop that basically goes from 1 all the way including to n, one by one. F is an accumulator that allows us to calculate or to save the product of all the instances of I. Once this condition is not satisfied, the loop will terminate and will give you the return value of f, which is the accumulator, into whatever method is being called. Let's compile and run this program to verify what we just said, which indeed is 120. Now, the very first step to transform this iterative-based method into a recursive method is to replace the loop to a while loop format. I know that a for loop and a while loop, they're both pre-test, so it doesn't really matter if you use a for loop or a while loop, but believe me, at this point, it's better if we just translate it into a while loop. Shall we? The only thing we're doing here, get the initialization outside of the loop, and the I++, the update, we incorporate into the body of the loop. This is equivalent to a for loop. The next step is to use the loop condition to create a recursive n base case. If you remember, a recursive case is the statements that would allow us to continue calculating some operations. Base case is when we stop. The next step is to use the loop condition to create a recursive and base case. The recursive case is the if statement, which consists on what is inside of the body of the loop. The base case, the else statement, is what is outside the loop. So the while loop will turn into an if statement, and the else will be what is outside of the loop. In other words, the base case. The next step is to supply a self-call in the if statement. Because it's the recursive case, here is where we need to incorporate our self-call. A self-call is the name of the method that we have. And you have to remember that if the return type is void, then you just need to call the method by itself. In this case, notice that our case has a return statement, a data type, which is an integer. Therefore, we need to use the return statement. The next step is to separate the local variables into a method arguments and update the calls. We need to be careful because local variables, like the ones that we see on line 7 and 8, they're no longer allowable in the recursive methods, primarily because they will be destroyed in every activation record. Therefore, every time you see local variables, we will provide those as an arguments or parameters. For example, here we have f and I. Might as well to incorporate them into the parameters as integer f, integer I. Having done that, we need to update our method calls, which are here. On line 12, we will provide f and we will provide I. In similar fashion, on the method call, we need to provide f and we need to provide I. Make sure you bring those with you when you go to the main method. If we compile this program and run it, we will find a similar answer that we were expecting. Notice that we don't have any loop and we are using some kind of recursion. It's a little bit too much, but it's working as a recursive call. Not as elegant as we want, but at least we are halfway through. And the next step is quite critical in order to achieve the elegancy of recursion, which is what we want primarily. The next step is to improve the number of arguments. Here's when we need to pay attention that instead of using irrelevant variables, like for example, the I that we're having here for counting, or other variable that is used as a counter, we can use the control variables to achieve our goal. Another way to improve our number of arguments is to interchange every time you see this postfix expressions, you will have to transform it into prefix expressions. The reason? Probably we already know that from the lecture. And it's because since these are activation records, we use something called the stack. And if you remember, a stack is first in, last out, and that will deal with memory management. Let's not focus on that right now. So let's go ahead and improve the number of arguments. For example, I. We don't really need to have I, since I is only a counter that helps the control variable n to achieve its goal. So instead of having I, notice that I starts at 1. So indeed, we can count in reverse order. Instead of going 1, 2, 3, 4, 5, we can go 5, 4, 3, 2, 1. Therefore, we can get rid of the I as a parameter and use n instead. So we can change here I for n, and since we're reducing our control variable, then it should be n minus minus. We don't need this parameter, and the only remaining part is this statement. Remember that I was the value of 1 initially, so one might as well just keep it that way. On our main, we don't need the value of I here and neither here. Let's go ahead and save this program, compile and run, and we see that we obtain the same result. As we already mentioned, every time you see this postfix, it can be achieved by doing infix, and we can incorporate this value in the parameter call. By compiling and running, results remain the same. The next step is to add the accumulator onto the self-call statement, which is the stack. Now notice every time someone tells you about an accumulator, like this one, that is where you can incorporate it into the method call, which is line 10. So in reality, we don't really need the value of f. Remember, the original purpose was to serve as an accumulator, so we no longer need this. But be careful, when you get rid of that one, the only thing we want to accumulate is the product of n, so that's why we have to incorporate into the recursive call. Since we don't have the accumulator anymore, we need to get rid of them from the parameters and the arguments calls. The last step is to negotiate what the method will return in the base case. Notice that the base case still wants to return the accumulator, but we no longer have it anymore. So here's where you need to negotiate what is the basic value you should return in this method. One of the tips that I can give you is, since the values deals with the product, the value does not affect the product is 1. So you can go ahead and just submit here 1. And that's one way to do it. I always like to see the last letter of this algorithm, which is the letter N, to also make it nicely. Remember that one of the objectives of recursion is to make very elegant code, and you can make it here. Notice that here, 1 less than or equal to n, it's okay to do it this way, but you can also simplify this expression by saying as long as n is greater than or equal to 1, which makes, semantically speaking, more sense. Otherwise, you're gonna return 1. You can still simplify even further by using the power of the conditional operator in Java, which can be translated as follows. If this condition is true, then we can provide this statement. Otherwise, we shall return 1. The end. If we compile this program and we run it, we will obtain the same result, but more elegant.